So we had kind of a rough start this morning with this handout called What Tools Do I Have? So find your 5.3.1 resource page. It's attached to today's assignment. If you can't find it, print another one. And let's start with A. You'll notice that these triangles are repeated in your textbook. And in your textbook, you were given the side lengths 7, 8, and 10. So go ahead and fill those in, 7, 8, and 10. And consider whether you have a tool that allows you to find the missing angles for this triangle. Now you have no evidence that it's a right triangle, so do not try to use a right triangle trigonometry tool. And right now, this is really a not enough information yet box, so we can move on to consider B. Well, this is a Pythagorean triple, so I can just go ahead and write 3, 4, 5 in here, and it is a right triangle, so I can use trig tools. The inverse tangent for this angle, let's call it A, and go ahead and enter that into your calculator by pushing the second tangent button and entering the ratio 4/3. We have approximately 53.13, and we're going to give that in degrees. And then for B, this other angle here, tangent of the ratio, or the inverse tangent of the ratio 3/4, and that's opposite over adjacent, equals B, and that is approximately, I'm entering 3/4, 36.87. And the directions for this task were to find the missing side lengths and missing angles. So there are 6 pieces of information for triangle B. So that triangle is complete. So triangle C is interesting. It's got a 60-degree angle in it. And I have the right to drop an altitude, which will be the perpendicular segment from the vertex angle to the base, and that'll give me a 30, 60, 90, which will be handy because I can then say that the distance between B and C is 7 and that the height has a value of 7 radical 3, and that looks a little bit like a 4, so let's try to clarify. 7 radical 3, H equals 7 radical 3. And that kind of allows me to move around this triangle. For example, if I knew this angle, I could figure out the last angle. So let's see if we can make it all the way around the triangle. So this distance here is now 13 because we've used 7 for BC. And we got 7 because we know that BC has to be half as long as AB because the 60, 30, 90 is a half equilateral triangle. So notice where the reflection would be here. So in my new triangle, it has a height of 7 radical 3 found by using these parts of the 30, 60, 90. And my side length of 13, I'd really like to know this angle. So what do I have? I have the opposite and the adjacent. So I can use tangent of some unknown angle equals 13 over 7 radical 3. And I can even use tangent of some other unknown angle. 7 radical 3 over 13. So it's looking like we could make our way all the way around this triangle. So go ahead and push those buttons. What is the inverse tangent for the quantity 13 divided by 7 radical 3? I've got about a 47-degree angle here. So if this angle is 47 degrees, then I've got a 60 and a 47. So the triangle sum theorem tells me 180 and let's remember that this one is 47 plus 30 in the larger triangle. So the triangle sum theorem tells me that 180 minus 60 minus 77 leaves me with 43. So is this approximately equal to 43? Let's try it. The inverse tangent of numerator 7 square root of 3 divided by 13 is indeed approximately 43 degrees. So if this is 20 and this guy, this missing side, is 14, then really all I need to find is this side, and I'll bet I have enough information here. So if m is approximately 43, how about if we use sine of 43? Equals 7 radical 3 over x. X sine of 43 equals 7 radical 3. X equals 7 radical 3 divided by sine of 43. So 7 times the square root of 3, that's a quantity, so I'm going to put that in parentheses in the numerator, divided by the sine of 43 is 17.78. So x is approximately 17.78. So we have now 3 side lengths and 3 angles. So those can be found by subdivision. And there's another example in here somewhere where we can use subdivision. But let's move on to D. We have 2 sides and an angle between them that we don't know. Maybe there's enough information, or maybe there isn't. Let's take a look. If we drop an altitude, is there a triangle here that we recognize? Well, there's a 90 and a 40. So that makes this a 50-degree angle. So is that usable information? Well, there's no good way to decide how this side was split in this case. We don't have a familiar triangle now that'll tell us that we've got a half or a square root of 3. So for this one, we have not enough information yet. And let's let's make our way around to C, where I have a right triangle, another angle, and a side. Well, hello 30, 60, 90 with a hypotenuse of 9. You must have a hypotenuse of 18. You must have a short leg of 9. And you must have a long leg of 9 square root 3. This is my 30, 60, 90 shortcut. And in F, two angles and a side not between them, but look, this becomes a 45, 45 and a 30, 60, 90. That's interesting. With a long side with a hypotenuse of 18, which makes this short leg 9, and this 9 square root 3. Well, and then this must be 9, because we're in a 45, 45. So this long side is 9 plus 9 square root 3. This side is 9 square root of 2. Can we make our way around to the missing angles? Well, 180 minus 30 minus 45. Triangle sum theorem tells us that this missing angle must be 105. So this is approximately 24.59, and this is approximately 12.73. And is there anything interesting that can happen here? We've now got a triangle that's a 48, 90, this whole angle must be 42. 42 minus 29 gives us this 13-degree angle here. The complement of 13 is 77. So there's enough information to get around triangle G using trig dimensions. Yes, I can finish this. Using trig and inverse trig. So how about H? Can I find side lengths if I just know the three angles? There is not enough information here in this 75, 90, what will that be? 90 minus 75, 75, 15, 90, and 45, 45. There are an infinite number of similar triangles. So not enough information, infinitely large, infinite number of similar triangles. So I would like you to finish the triangle given in G. And I would like you to have a copy of all of these finished triangles and the work done to finish them.